So let's quickly review what we've been doing last class. So specifically we said that the cross-coupled oscillator that we originally looked at, that had an NMOS cross-coupled pair, right, with an NMOS current source. You can actually find out very different analogous ways of building the same circuit with a combination of NMOS and PMOS devices. For example, you could have a PMOS cross-coupled pair with a PMOS current source, okay, or you could also have the other version, which is the NMOS cross-coupled pair but with a PMOS current source, and finally you could have a PMOS cross-coupled pair with an NMOS current source. So all four types are possible, okay. There is nothing inherently good or bad about either one of these, but there may be certain cases where you might prefer one or the other. Can you think of any reasons why you might prefer one over the other? As it so happens, so far we haven't seen much to choose between the two, except for the fact that the PMOS will be 3 times larger than the NMOS for the same negative resistance, and therefore it will have larger parasitic capacitance and smaller tuning range. That is the number one difference we have seen in the cross-coupled pair. As far as the bias is concerned, what is the reason for choosing one over the other? It could again be the same reason. The NMOS, for a given VD sat, the NMOS will be 3 times smaller, right? So you are going to give a certain headroom for the current source. The NMOS will be 3 times smaller, therefore for reasons of lower area you might decide to go with the NMOS, okay. And we said this is actually a voltage controlled oscillator, not just a standalone oscillator but a voltage controlled oscillator, which means you are going to use it, instead of just letting it run by itself, you are going to run it inside a PLL, okay, where the PLL feedback sets the control voltage and therefore sets the frequency of the oscillator. And you want the behavior to be linear to place it in the PLL. In our particular case, with the cross-coupled oscillator with the simple LC tank, parallel LC tank, the frequency of oscillation is 1 over 2 pi root LC. However, we also know apart from the fixed capacitance, we might have some parasitic capacitance from either the transistor, the fixed capacitor itself, or the inductor. Okay, all these sources will give you parasitic capacitance, and therefore the actual expression is 1 over root L times C plus Cp. Okay, that is the real tuning, that is the real oscillation frequency. Then we said we want to change the frequency as a function of the DC voltage, and obviously the inductance is much harder to control as a function of a DC voltage, whereas the capacitance is quite straightforward. We do know devices which do that, okay. Those are called varactors, okay, voltage variable capacitors, and the simplest example is this PN junction, a reverse bias PN junction, where the depletion region width is a function of the DC voltage applied. The other example is a MOSFET. So you use either the transition from accumulation to depletion or from depletion to inversion. Okay, one of these two transitions you use, and it's very common in modern processes to have a dedicated varactor which is optimized for this particular behavior. So in other words, we said that if you take a varactor, in fact if you take a MOS varactor and look at the capacitance as a function of the DC voltage, okay, we know that at very high voltages the capacitance is going to be WLC aux, okay, and at some voltage what happens, around Vt the device inverts, correct, around the threshold voltage the device inverts. So before that, you only have a depletion region. So you have some, okay. At very large negative voltages, you again have accumulation, WLCox. You have some behavior like this, okay, in the capacitance. But it is obviously not convenient to use this device directly because you are using it in a feedback loop, and therefore you want the capacitance behavior with voltage to not be non-monotonic. Okay, if it's non-monotonic, in other words, if it has different slopes, okay, and different signs in the slope, your feedback sign could change. You have to be very careful, right? Obviously, in one direction, if you increase the voltage, the capacitance increases. On the other side, if you decrease the voltage, the capacitance increases. Obviously, this is a problem. Okay? So therefore, it is quite common to actually create a device which is completely monotonic. For example, suppose I take this guy and I want to prevent, let us say, the inversion region from, I want to prevent the device from inverting. What do I need to do? Let us say this is an NMOS device. N plus P well, right? This is my NMOS device. I want to prevent this device from inverting. Huh? P well doped heavily. Okay, that is one possibility. Can you ever prevent it from inverting? If the PL is doped heavily, what will happen? Huh? Threshold voltage will increase, right? But you want to completely prevent it from happening. And by the way, unfortunately the problem is this, okay? In a normal PMOS, this is actually the P substrate. You can't randomly change the doping of the substrate. If it's a well, you can, okay, but not the substrate. Any other ways you can prevent it from inverting? So what do you want to do? You want to have inversion and you want to have depletion. Correct? What are the conditions for, you want to have accumulation and depletion. What are the conditions for accumulation, depletion? Okay, let's ask it in a different way. What is the condition for inversion? Gate to bulk goes more than VTH, okay. But what causes inversion really? I mean, okay, what happens during inversion? A channel is formed, right? In this case it's an NMOS, an N channel is formed under the gate, correct? How do you prevent an N channel from being, okay, where does the charge for the N channel come from? From the bulk, okay. So how do you prevent it from forming? Keep the same voltage for gate and bulk. Okay, but in this case we want to use the gate to bulk DC voltage. Okay, which two nodes does the channel form between? Between the drain and source, correct? Between the drain and source, right? And I have the P substrate. Okay, I want to create a capacitance between any two nodes, and I want to prevent it from inverting. So you are right. You are on the right track. So what would you do if you had to prevent the channel from forming? You are right. It is from the substrate in this case. So what would you do? So obviously you cannot have a P substrate. You cannot have a P well. Okay, to prevent the device from inverting. So if you want to prevent the device from inverting, what you need to do is to actually put two n plus regions inside an n well. Okay? In fact, we'll probably do this. This would be one node for your varactor. This is why I said it's very common to have more specialized devices. But really this is not a particularly specialized device. What you're going to do is, you have an n well already as part of the process which you use for the PMOS. Okay, you already have the n plus diffusions which you use for the NMOS. You're just putting the two together to actually create a device which will never invert. Of course it can accumulate, okay, and depending on the voltage there will be a capacitance change as a function of voltage. So we'll have this region, but then it will continue like this. Okay, that is what will happen with this device. Okay. Similarly, you can think of other ways to actually create these kinds of voltage variable capacitors. For example, we talked about a PN junction. Okay. I can actually create, there are specialized processors available where there are specialized PN junctions to give you very large Cmax by Cmin, as well as you try to get a more linear behavior of frequency versus control voltage, right? So you dope the junctions as well as grade the doping of the junctions to get a better behavior, okay, for specialized use as a varactor. All of these things are possible in different, flavors of the processors that you work with. Okay, it really depends on which. Many of these modern pure CMOS processors may not have a PN junction diode dedicated for this. You may be much better off just using the MOS varactor. Okay. However, there are cases where the MOS varactor may not have enough Q, or rather you can get a PN junction with a better Q than a MOS varactor. Maybe a lower Cmax by Cmin but a better Q. That is also possible. Okay. So you will obviously have to evaluate specifically for your case which works best. Okay. Okay. So now back to our the problem that we were looking at. So we said that because of the tuning range which we want to get from the fixed capacitance, the parasitic capacitance becomes a lot more significant. Okay. And the actual Cmax by Cmin is actually Cp plus Cmax of the device by Cp plus Cmin of the device now. It's smaller than the raw tuning range. Okay. Now, having seen that, we decided to look, one of you suggested this architecture where instead of using only an NMOS cross-coupled pair, we use an NMOS and a PMOS cross-coupled pair. Right? And one of you said, for example, that it's actually reuse of current, right? And I showed you an example of why it really does not reuse current. You happen to be reusing current to actually get, what was suggested was you're reusing current to get more negative resistance from the PMOS and the NMOS. But I gave the example of an NMOS cross-coupled pair where you actually just make it twice the size. You will get negative resistance will become half, more dominant, right? So that is not necessarily a reason with the exact same tuning range hit. Okay. So that is not the reason why anybody would move to this particular topology, circuit topology. Then we said, okay, we want to compare the two directly. So we said in one case, for example, in this particular case, we are using a single RLC tank. In the case of the NMOS, we are using, two RLC tanks. So I said, okay, so let us try to normalize the two in terms of area. So what I'm going to do is, I'm going to use the same RLC tank in both. So in other words, in the NMOS case, I'll have L by 2, 2C and R by 2 on either side. Okay. That way, I will normalize the area, normalize the inductance value, capacitance value, even the tuning range now. As far as the raw device capacitance, the tuning capacitance goes, that is also the same. Right? And as in terms of the parasitic capacitance is also the same. Right? Because the device size in one case is 3x So let us say this is 3CP and CP, so this is 3W and W, so I have 4W. To get twice the GM with the simple cross-coupled pair, I also need to make the width 4 times of the NMOS. So really the parasitic capacitance is also the same. So the thing that is different between the two, okay, will need to be tracked down in a little bit more detail. So let us build up this guy. So to refresh, let us look at the NMOS cross-coupled pair again. Okay. So okay, this is my RLC tank. I have a current source IT going through this VCO. Okay. And maybe this has some certain GMN. Okay. How did I find out the oscillation amplitude of this? So what I did was, I said the NMOS cross-coupled pair, okay, is switching at the rate of the oscillation frequency. Switches at, I'll call it F0. Okay. The other thing we said was the positive feedback due to cross coupling, okay, makes the switches switch very fast, almost instantaneously. Okay. And so what happens is, during half the cycle you have IT current flowing through one side, so I call this M1 and M2. During one half cycle, M1 is conducting, current is flowing through M1, all of IT is flowing through M1. During the other half cycle, all of IT is flowing through M2. Okay. And M1 is off. So if you had to, so what we'll do is, we'll split it up as a half circuit. That's what we did before, we'll analyze it exactly the same way. Split it up as a half circuit so that we can get V1 and V2. Okay. So if you had to look at the current through the left half, maybe it does this. Okay. So this is I1 as a function of time. So it goes between IT and 0 with a time period 1 over F0. Okay. So if you had to redraw the half circuit for this, you will have L by 2. The capacitance will have to be split as two capacitors in series with a virtual ground in between. So you'll have 2C, oscillation frequency will remain the same. This will become R by 2. Is that clear? Okay. And this is V1. Okay. And we said that the current has infinite number of harmonics, but the RLC tank has a very specific frequency behavior. It will choose only the fundamental that we are interested in. Okay. So we first split up the current into its harmonics. So we have the DC current of IT by 2 plus what do we have? This is a square wave going between 0 and IT. So what happens? 2 by pi into is this cos or sine? Sine omega naught t plus what? What is the next term? 1 by 3 this is your Fourier series for the current. Okay. Then what happens? So the fundamental that we are interested in, V1, okay, is I1 of omega naught times R by 2. Right? We have R by 2 here. What is this? 2 by pi, sorry. Okay, it's IT by 2, IT into half plus 2 by pi and so on. So this is 2 by pi IT into, so this is amplitude of V1 is what we are interested in. Or let us just write the full expression, why not? 2 by pi IT sin omega naught t. So because we are interested only in this term times R by 2, which is okay. So ITR by pi sin omega naught t. Now of course if you look at the differential signal, you have V2 on the other side. So the differential output signal is going to have an amplitude of 2 ITR by pi sin omega naught t. Okay. Now note a small difference from what we had done before. The reason I wanted to do this again was because it's slightly different from what we had done before. Yeah. Earlier we had got 4 by pi ITR. The reason for that is because our tank we had RLC on either side. Okay, that is probably not the best way to do it if you want to compare these two circuits. Okay, that is why we have come back to this 2 ITR by pi. This is more or less the accepted way of representing the amplitude of the NMOS cross coupled pair. Okay, so now let us draw the PMOS cross coupled pair and figure out what that looks like. Okay, so now I have the same current IT. I have the same current IT flowing through this particular oscillator, and let us say I have normalized it such that it has the same negative resistance also. Okay, so how do you analyze this circuit? In the previous case we said that the NMOS cross coupled pair has a strong positive feedback, current is switching on either side very quickly, right? Okay, what would you say about this case? should be exactly the same, right? So you have these two NMOSFET switching, right? Depending on the waveforms on this side. So let us say the two waveforms V1 and V2 have this phase. Okay? So let us look at the first half cycle. Let us look at this half cycle. What happens? So let me name this guy M1, M2, M3 and M4. Okay? Among M1 and M2, which one is on? M2 is on. Okay? Among M3 and M4, which one is on? M3, right? Note that difference. Okay, because it's a PMOS. So which way does the current flow? So the current actually flows through the tank in this way. Okay? In the first half cycle. What happens in the second half cycle? Current will flow the other way. Okay? Is that clear? Pretty straightforward, right? Okay. So now, if you had to draw an equivalent circuit across the RLC tank, what would that look like? So let us say I'm going to plot the current through the RLC tank. Okay? As a function of time. So what happens? let me say I'm going to take this direction. That is not a problem. Okay. So why is the amplitude of the VCO itself important? So as it turns out, it is the amplitude of the VCO needs to be large because of signal to noise ratio at the output of the VCO itself. Okay. So far we have been looking at the signal to noise ratio of different kinds of circuits. The VCO also has a certain concern about noise behavior, as in if you are designing VCO, you are also concerned about noise. In fact, you are very concerned about noise. The reason is this, right? The amplitude the amplitude of the VCO itself, okay, can be quite large. You can easily get, depending on how you choose the bias current and the size of the inductor, right, or the size of the parallel resistance, effective value of the parallel resistance, you can easily get a few hundred millivolts or maybe more than a volt. That is very straightforward. And you can increase this to 0 to VDD. You can make this smaller if you want. You can manipulate this very easily, right, depending on what you need at the mixer. And at the end of the day, what does the mixer do with the output of this LO signal? What does the mixer do? So you have an LO sinusoid coming into the mixer. What does the mixer do? Let's look at an active mixer. What does the mixer switching pad do? You are explaining what the mixer does. That is not what I want. I am asking you very specifically, what does the mixer do to the input LO signal? I have an LO signal, VLO sin omega LOT, going into the LO port of a mixer, right? What does the mixer do? How did we analyze the mixer? Whether it is an active mixer or a passive mixer. What did we do? We applied this to a pair of switches, right? What is the switching function we used? Let's take the active mixer. We said the output current is just going to be a square wave. So in other words, it has no relation to the input amplitude. The behavior of the mixer does not directly depend on the input amplitude. As long as the input signal switches the two currents completely and quickly, right? We don't care about even if the amplitude has small imperfections, we don't care. Right? So let us say you required for linearity concerns, you wanted a 1 volt sinusoid at the LO port. If this was 1.001, do you think anything will happen to the operation of the mixer? Of course not. It will look exactly the same as before. Right? It will not look any different at all. Linearity will also be practically the same. Okay? So really, the amplitude of the VCO, okay, or imperfections in the amplitude of the VCO is of very little concern. What is more important is the phase of the VCO, the zero crossings, right? These are very critical for a number of reasons. Obviously, the mixer switches at exactly the zero crossing, right? You want the zero crossing to be fast, maybe for certain requirements in the mixer, okay? So instead of a sine wave, you may want a square wave and so on. But really, whether you look at a sine wave or a square wave, you are talking about preserving exact zero crossings. Okay, that is the number one thing we are interested in from the VCO. Okay, which is why when we started off with, I already told you there may be some VCOs which give you sinusoids, some VCO which give you square waves. We are really not interested in directly distinguishing between the two. In many cases, even when you have a sinusoidal oscillator, you quite often convert it to a square wave and then use it. Even when you embed it inside a PLL, the PLL is interested only in the phase of the signal. It is not interested in the amplitude of the signal. Okay? So at the end of the day, we are interested in the phase of the signal. And if this phase, in other words, if these zero crossings of the VCO signal have imperfections, we are really, really worried about them. Okay? Because any imperfections in the zero crossings will manifest themselves in the operation of the mixer and in the operation of the overall transceiver. Okay? And this particular imperfection these imperfections in the zero crossing, okay, in the time domain we call them jitter. We call this jitter in the time domain. Okay, and we call this phase noise in the frequency domain. Okay, so what do we mean by jitter? So let me take a square wave. Okay, let me take a square wave. For example, I want 0, t by 2, t, and so on. However, if this zero crossing happened before, maybe this zero crossing happened after, that is very well possible, right? And what you will find is that at every zero crossing, because of noise in the circuit, okay, you will find that the zero crossing does not happen exactly where you want it to. It happens maybe slightly before or slightly after. We have seen cases like this before. For example, in the mixer, right, the differential pair noise actually changed the switching instant. Okay, we expect something similar to be at play here. Noise from the devices to actually change your ideal zero crossing. Okay. So at every zero crossing you have this problem. Okay. How do you characterize this? So maybe you have delta T2, delta T1, delta T3, delta T4, and so on. Now you need to find a way to characterize this jitter, as we called it. How do you characterize this jitter? First of all, it's based on noise. So the only way of characterizing it is in statistical form, right? So you can talk about things like RMS jitter, right? So you can talk about terms like RMS jitter and so on. There is period to period jitter and all kinds of ways to characterize this. Okay, but the important thing to understand is that you are doing a statistical characterization of this jitter. Now, suppose I want to characterize it in the frequency domain. Okay, the reason is simple. Okay, in the case of transceivers, we are really looking at circuits almost always in the frequency domain, or rather, the signal we are trying to process is in the frequency domain. The circuit analysis itself may happen in the time domain, but the signal itself you are trying to move it in the frequency domain. You are looking at noise, folding over, and so on, right? If you look at this, these are actually two equivalent representations of the noise in the let's say the oscillator in any signal, in any timing signal. There are certain set of applications where you are interested in the RMS in the jitter in the time domain characterization. Okay, there are, for example, if you are trying to transmit a baseband signal, a switching signal from one chip to another. Okay, simple example is let us say USB connection. Okay, and you are transferring a file, you are worried about the timing. Similarly, maybe a display card, like you have a PCI Express card for a display. It's all the same thing, right? Many of these applications, you are trying to transmit a switching signal from one chip to another, right? In those cases, the switching instants are very important because you are actually transmitting a baseband signal directly. You are not transmitting a modulated signal. You are not upconverting it. Okay. In our case, in a wireless transceiver, you are not looking at the time domain. We are looking at the frequency domain. Okay. Therefore, it makes sense to look at the noise in the phase of the signal, because at the end of the day, remember, we are going to extract the amplitude and phase of the signal that we are demodulating or transmitting, one of the two. And in the frequency domain, okay, if you have an ideal oscillator, just like we drew an ideal square wave, let us take an ideal oscillator. Okay, an ideal oscillator, a cosine function, okay, will look like this. Okay, it will have a certain power and so on. If your zero crossings of the sinusoid are imperfect, what will that look like? So in black, I have actually drawn some a cos omega naught t. Correct? Now let us say in red color, I want to draw a signal with some phase noise. First of all, what will be the mathematical representation of a system with phase noise? We have already figured out that the amplitude noise does not matter, so we'll just ignore it completely. So we'll just call it a cos omega naught t plus some phi of t. Let's call it phi of t. Right? Obviously, this phi of t is actually, it's a time varying function. It depends on noise and it is going to change the zero crossing. How do you represent that in the frequency domain? Okay, how do you generate the frequency from the phase? Differentiation, right? The frequency will be d phi by dt. Okay, when you had an original, the original sinusoid a cos omega naught t, the total phase at any time is omega naught t. You are going to differentiate that to get the frequency, angular frequency omega naught. Okay. Similarly, let's take this omega naught t plus phi of t, differentiate it. You are going to get omega naught plus d phi by dt. Okay. What will the d phi by dt look like? We don't know the exact characteristics of it, but you will no longer have a fixed impulse. Okay. So what you will get? Probably something like this. Okay. You will get what are called noise sidebands. Around what you expected was an ideal impulse. Okay. How do we characterize this? So now, for the next few classes, we are going to worry about this particular noise characterization of the VCO, because this is extremely important. Okay, in VCO design, in PLL design, and in any transceiver. Okay. The reason why it is very important is because the phase of the upconverted signal, the phase of your true RF signal, let's say in your transmitter, depends primarily on the phase of the LO signal. If your LO signal has noise in the phase, that will get directly translated to your output RF signal. Right? So this is extremely important. So you have to worry about this in any transceiver. Okay? Okay? So the way we do this, because we need to look at a couple of other things before we look at phase noise in a lot of detail. What I'll tell you is, phase noise itself is going to be characterized as some kind of SNR. Okay? So you are not only interested in the phase noise, or let us say it is characterized as a negative SNR. Okay? So as some kind of noise to signal ratio. Right? What is the signal power here? Signal power is A squared in this case. A is the amplitude, so A by root 2 is the RMS, right? So A squared by 2, right? Technically. Okay? So signal power is known. What is the noise power? We'll have to integrate the area under these noise curves, or rather we will have to specify maybe a spot SNR or a spot phase noise. Okay. Okay. And compare it to your signal power at F0. That is normally the way to characterize phase noise. Now, having known so much, okay, knowing that phase noise is characterized as noise to signal ratio, can you tell me if the NMOS cross coupled pair will be better or the PMOS cross or the complementary VCO will be better, and why? What is the only difference between the NMOS cross-coupled and the complementary cross-coupled VCOs? Amplitude. Which is larger amplitude? NMOS PMOS. The complementary cross-coupled pair has a larger amplitude for a given current. Correct? Everything else is the same. Everything else being the same, it has twice the amplitude. Which VCO do you expect to have better phase noise? The one with the larger amplitude will have lower phase noise. Remember that it's characterized as a negative SNR. So a circuit which has a lower phase noise is considered to be a better circuit. It has lower noise. Okay? And normally it's expressed in dB terms. Look at these circuits, as we try to understand phase noise, we will come up with the exact expression for the dependence of how phase noise, dependent of phase noise on the signal power, and so on. But definitely a circuit which has a larger amplitude seems like it will have better phase noise. Correct? For example, I take a certain VCO, maybe it has an amplitude of 500 millivolts. Okay? I double the current. Okay? I double the current. What happens to the signal power? I expect that to double also. Okay? What do you expect the noise to do? The noise should get lower. The noise to signal ratio should actually get lower. That you definitely expect. So by that characterization, your phase noise for that second VCO should actually be better. Okay? Okay, so now let us do something quickly in the remaining couple of minutes we have. Let us try to list down the important parameters of a VCO. Okay? Or important metrics of a VCO. What are the important metrics? Well, output frequency, definitely. Okay. What else? Maybe power consumption. What else? Amplitude. What else? Phase noise, okay, of course. What else? Tuning range, okay. Anything else? Output frequency, power consumption, amplitude, phase noise, tuning range, anything else? Sensitivity, what is that? How do you characterize the sensitivity of a VCO? What do you mean by sensitivity, first of all? Sensitivity to what? With respect to which one? Okay, with respect to the control voltage? Very good. So, of course, KVCO is a very important parameter, right? The basic equation of the VCO itself depends on the KVCO. So, it better be an important metric. What else? Anything else? Okay, So right now we have said that he mentioned the word sensitivity, right, to the control voltage. Now as it so happens, if you try to change the supply of the VCO, that will also change the tuning of the frequency of the VCO, maybe to a much smaller extent, but it will change. So you have terms like supply pushing or pulling. To represent the sensitivity of the VCO to the supply. Okay, this could be either a fixed variation. For example, you want a power supply voltage of maybe 1.2 volts, but maybe the power management IC that is actually producing this voltage guarantees maybe 1.15 to 1.25. If you change this from 1.2 to 1.25, if the frequency of your VCO changes, that is an important parameter. Okay. Number two, the power supply is not just a pure DC voltage, it comes with its own noise, because the power management IC may have certain switching characteristics, it has certain devices, so it may come with either device noise or it may come with some unwanted signal on top of it. Okay, maybe some spurious tones at the switching frequency of the power management IC. Okay, so these are all things which will affect the behavior of the VCO, and you will need to characterize how sensitive your VCO is to these things. Okay, so let us stop here, and over the next couple of classes we'll look at phase noise in a lot of detail. Okay, so our next couple of classes is going to be devoted to that, because we have more or less looked at many of the other things. We have looked at the tuning range, right? There's not much to it. Amplitude we have looked at in a lot of detail. KVCO you will look at it when you actually design PLLs. Okay, what decides the KVCO of the oscillator? It depends on the varactor characteristic, right? If the varactor has a very large change in capacitance for a very small voltage, that will give you a very large KVCO. The frequency will also change by a lot, right? So it primarily just depends on the capacitance characteristics. Okay, so depending on how you design your capacitance, right, in the tank, you can design it for a certain KVCO. Okay, the phase noise on the other hand is a little bit more involved, as with the noise of every circuit we have seen in this course. So we will look at it over the next couple of classes. After we do that, we will come back and look at maybe a different class of oscillators among LC oscillators. Okay, because cross-coupled oscillators are not the only oscillators that you can design using LC tanks. They happen to be the most popular ones, but we'll look at the other kinds when we come back.